Hello and welcome to EE233. I'm your instructor, Gregory Myers. In this video, we're going to take a look at another example in our series focusing on the fundamentals of the C programming language and as part of our fundamentals demo. In this case, you should get a copy of your formatting_doubles.c file. And if you have not yet done so or do not have access to it, you can take just a second to do a screen capture and then create these snippets of code. There are actually two functions in this particular example. The first one deals with formatting the doubles, and the second one deals with an approximation of pi using series. So to begin with, what we want to do is we want to go ahead and copy our two function prototypes over to our fundamentals.c, and we want to add it to the bottom of the list here. Take just a second to note that our formatting doubles function matches some of our previous examples where we had a void input argument and a void output argument, essentially meaning that nothing was put into the function, nor was anything returned, but rather the approximate pi function accepts no input arguments, but returns a double. Also take a look that in this particular example, we also have a constant that we define as pi. Now, pi is available in our math.h, but I'd like for us to see a couple of things here. Number one is how we go about, once again, defining pi, but also the fact that we can actually use a function to assign a value to a constant. In this case, what we're going to do is we're going to use our approximate pi function to assign a value to pi. Continuing on with that, let's go ahead and copy over our function implementations. In this case, we're going to go ahead and copy over the help, or rather the comments, excuse me, as well as the approximate pi function. And we'll go ahead and add it now to the bottom of our list, which has grown quite extensively over these videos. And then just a little minor cleanup with the spaces just to be consistent. And once again, you'll notice that we have a void input argument and a void output argument, which means that everything we plan on doing has to be inside of the function. Now at this point, if you've had working code before, and we assume that this example is also working C snippet, you should build it and you should get a successful build. And what we'd like to do now is we'd like to turn our attention to the main, and we will once again turn on and turn off functions. So in this case, we're going to turn off our formatting integers, and we are going to turn on our formatting doubles function. And so here we're just simply going to make a call to the format doubles demo. Now, it's important to note that all of this happens, the assignment of pi to a constant happens before we actually call the formatting doubles. So therefore, if you take a look down in the formatting doubles function, you'll actually see that we can leverage the pi constant. Now, we could have simply made multiple calls to the approximate pi function, but once again, the purpose of this is to show you that you can use a constant and have that constant derived from a function. Also note that in the approximate pi function, we have a couple of new things going on, particularly a for loop. We haven't really talked too much about this, but essentially the for loop then is used to seed or to run this alternating series, or the summation of this alternating series. Now I've provided you the link for the Leibniz formula for pi. It's simply a Wikipedia article, and you'll notice here in this particular alternating series that essentially if you multiply both sides by 4, you get the approximation for pi. If you'll note, I've done the same thing here, alternating the sign every iteration of the for loop, and also then at the end, multiplying the sum times 4. And so in this particular case, this function accepts no input arguments, but will return a double that is an approximation of pi based on the number of terms that we have selected. And in this case, I've simply hard-coded this value in. And if you notice, we are incrementing by 2, once again, to fulfill the mathematical formula for the Leibniz formula, or rather to fulfill that pattern in the Leibniz formula for pi. All right, so without further ado, let's go ahead and build it one more time. We can go ahead and close our formatting doubles, and we should be ready to test this now in the command window. Okay, so going out to the command window, we will change directories, however you need to get there, over to our fundamentals demo, back into our distribution, debug, and then our MinGW folder. And there you go, you see your fundamentals demo. Now, this one's going to be fairly simple. I encourage you to play around with this. Essentially what we want to do is we want to take a look at how doubles then can be formatted. And if you'll notice here, I've just gotten us started. I've started with the %f left by itself, if you notice, is going to provide us 1, 2, 3, 4, 5, 6, 7, 8 places. That includes the decimal point. So by default, that is going to be 8. If we want to have more places, then what we do is we simply provide then a larger number here. So in this case, what we'll do, we'll start off by putting in something like 16, just so that we can see the behavior. And so if I go ahead and build this and then rerun it, you'll see that I get a total of 16 spaces. So essentially what I've done are 16 characters. So what I've done is essentially padded the front of the number, and that wasn't quite what we wanted. Instead, what we want to do is we want to control both the total number of digits, including the decimal, but we also want to have some control of how many places after the decimal point we print. So in this case, 16 didn't quite get us what we want. Let's instead try to focus on splitting this up a little bit. And we already know, for instance, that we would expect, let's say, a total of 16. Let's say, though, that we want to assign 8 of them after the decimal place. And so if we build this one more time, then let's see what we get here. You'll notice that I have my total of 16 spaces here, but this time around, let's count 1, 2, 3, 4, 5, 6, 7, 8. You can see here that I'm sort of controlling now how many places after the decimal place I would like to show. And we can continue to play with this quite a bit here. And so, for instance, if we want to increase this even to 12, it doesn't change the total number of places. It just changes the number after the decimal point. And you can see here that I am getting increasing precision here. Now, this does not mean that I've changed the accuracy of my pi value. That's a separate question, and you'll control that by simply increasing the count here, or increasing the number of iterations that this for loop uses. By the way, it should be noted that if you notice how quick this runs, if you take a second to note here how many iterations of this for loop we're actually running. So you're starting at 1, and since you're incrementing by 3, it's going to be 1, 3, 5, and so on. So you're doing, in this case, you're going to be doing around 10,000 iterations. Pretty impressive given the fact how quickly this runs. We can do the same example, for instance, in MATLAB, and you'll see a noticeable delay. The rest of these examples just simply play around with this format spec a little bit, and you'll see here that I have a total of 5 places in this next example here. So that's why we have a single space in front of this 3.14. So there's 1, 2, 3, 4, 5 total, and with 2 places after the decimal being assigned now to the excuse me, being two places after the decimal being assigned. And if you happen to choose too few, so in this case, I chose only 3 total characters or 3 total positions, in which case would not be enough. It's essentially just ignored and focuses only then on the number of places after the decimal point. So you can actually do something like this. So if we focus back here on our 16 and 12, I can in fact just simply drop the 16 altogether. And then if I build this, what happens is I essentially just ignore the number of places total, and instead I'll focus on just the number of places after the decimal place. So in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Probably would have been better for me to pick a example with less values than 12, but hopefully you see the point. And then also you'll notice here that as I get further down here, I have also increased in this example here, 5, 3, I've increased then the number of places after the decimal point, which brings us to our last example where in fact I've just simply hard-coded a value in here, sample of 0.1234. And you'll notice here that I have in fact only given myself 4 slots to work with. And so essentially, since the first slot is going to be 0, rather than eliminating it altogether, it simply just focuses then on the 2 on the right. So essentially, if you notice here that I have assigned a value of 0, even though I wasn't explicitly in the value that I have attempting to print. So it's going to, when it's a decimal less than or between 0 and 1, or actually, yes, sorry, between 0 and 1, you're going to essentially prepad that with a 0. So there's many, many more examples that we can give here. This is just meant to be a starting point. We will come back to this in the future many, many more times. But I just wanted to get us started with the process of formatting doubles. Also wanted to show you how you can approximate pi in addition to using the values of pi that are found in math.h. And so let's take just a second to go ahead and include our math.h so that you know where those values could be found, even though we aren't going to technically use them. So in this case, you can right click and navigate to the source. And in this case, I'm going to look for pi, and you'll see that there's a couple of different values of pi, pi over 2, pi over 4, and then so on. So hopefully, once again, you found this video useful. If you got any questions or comments, don't hesitate to email me, and thank you for watching.